Okay, moving right along here into chapter 9, we're going to discuss a little further into chemical equilibrium. We'll pick up at that concept I left off on in the last section, where we start to think about what the equilibrium constant value actually says about whether we're favoring reactants, favoring products, or pretty well near equal at equilibrium. So in the last section, we discussed calculating the equilibrium constant. Now we're going to actually discuss using these equilibrium constants now that we know the values. And again, as I hinted to at the end of the last section, these equilibrium constant values have much to tell about the position of equilibrium, what's favored when we achieve equilibrium in a given reversible reaction. Okay, so the values for equilibrium constants can be very large numbers or very small numbers. They cannot be smaller than 0. We cannot have negative values because we cannot have negative concentrations. The least amount of anything you can have is 0 molar concentration. So therefore, if we've got numerators and denominators in a fraction of equilibrium constant type, we cannot have negative numbers. So the size of the Kc value, whether it's a small number, so a negative exponent, yes, but a negative value, no, or a large number, a positive exponent that's very large, will tell us what the position of equilibrium is when we reach that particular situation where the forward rate of reaction and reverse rate of reaction are equal. So if the Kc indicates that there's more products than reactants. Remember, the products are in the numerator, so that would give a Kc that's a very large number, so maybe 10 to the positive 5, 10 to the positive 10, something very large. Or we might have a situation where there are more reactants than products, so Kc itself would be small because the reactants are in the denominator, the products are in the numerator. If there's relatively little product, lots of reactant still remaining at equilibrium, then the Kc is going to be a small number, maybe 10 to the negative 5 or 10 to the negative 10 exponent. But again, positive values always, just the exponent would tell us whether we're large or small. If we're in the, say, 500 to 0.005, 500ths or 5,000ths or whatever we might want to think about there, that's where we're not really greatly favoring products or reactants. But when we get up into those positive 5 exponents, where we have a Kc that's large and we're favoring products, or 10 to the negative 5 exponents, or a larger negative number would indicate a very small Kc, and therefore products being made in a very small amount compared to the reactants. Okay, so if we examine first a case where a Kc is large, and again, large is a fairly ambiguous term, right? So in this case, we'll see that we're talking about something like 340. So again, based on what I've been saying, that's not terribly large for an equilibrium constant, but I guess it's significantly greater than 1, which is what we'd expect as an equilibrium constant for something where there's roughly equal product and reactant concentrations. So what that Kc that's large indicates is the forward reaction produced a large amount of products as we were tending toward equilibrium, and then the reverse reaction didn't use up too much of those products to reform reactants once we equalize those rates. So the equilibrium mixture, the position of equilibrium, as I've been saying, is such that there are mostly products at equilibrium and not as much in the way of reactants remaining. So if we look at this given reaction, 2 moles of sulfur dioxide gas plus 1 mole of oxygen gas in equilibrium with 2 moles of sulfur trioxide gas, well, we see the Kc would be the SO3 raised to the second power because of its coefficient of 2, divided by the SO2 raised to the second power because of its coefficient of 2, multiplied by the O2 to the 1 power because of its coefficient of 1 that's not shown. And then again, of course, its exponent's not shown either. So in this case, because we get a large number, relatively speaking, that means we have mostly products, relatively little reactant left over, and therefore we have a Kc that's significantly greater than 1. All right, so here we see that in sort of a bar graph form. So when we start with essentially all reactants, right? And we have twice as much of the SO2 as the O2. roughly speaking. Again, these are concentrations in moles per liter, but without actual numbers, so we're just showing it sort of graphically here. And then once we achieve equilibrium, we still have some SO2, we still have some O2, but we have mostly SO3, mostly product at equilibrium for this particular example. So that's what we'd expect anytime we see a large Kc. And again, a large Kc for our course, I guess we'll say it's greater than 100 would be what we'll consider large, and less than 100th is what we'll consider small. Okay, so looking at that small case, so Kc is small here. When a reaction has a small equilibrium constant, it means that the reverse reaction converted a lot of product back to reactants. And so the equilibrium mixture, the position of equilibrium, is such that we have mostly reactants and not much in the way of products at the equilibrium position. So for the reaction here, we see N2 gas, 1 mole, reacts with 1 mole of O2 gas to form 2 moles of NO gas. And again, the double arrows show us it's a reversible reaction. If we were to write the Kc, of course, we see it on the slide here. NO, the product, raised to the second power, its coefficient of 2, divided by N2, raised to the 1 power, which we don't show, and O2 raised to the 1 power, which we don't show. Again, since there's relatively little in the way of products, that numerator is going to be a small number, and even though it's squared, it's not going to be a very large number at all. The denominator will be much larger because the N2 and O2 concentrations are much more significant than the NO concentration at equilibrium, and we get a value of 2 times 10 to the minus 9. So that's a small number, right? So that's what we're looking at. It's still a positive 2. It would always be a positive concentration, but a large negative exponent is what we're looking for in the way of a small Kc, indicating that we have mostly reactants, almost no product at equilibrium. And here we see that graphically, again, without any numbers, just showing the concentration in moles per liter along the y-axis. Initially, we have just the N2 and the O2 present. As we tend toward equilibrium here, now we have used up just a little bit of N2 and a little bit of O2, and we've made a very small amount of NO. It's not quite right based on the graph, but I hope it at least gives you a visual of when we were talking about being mostly reactant still when a small Kc is observed. So almost no product, mostly unreacted, or reactants. Of course, they're reacting, but the rate at which the reactants are reacting in the forward direction is much less than the rate at which the products are reacting in the reverse reaction until we achieve equilibrium and the rates equal out, and then we're left at this position where we have mostly reactant, very little product. Okay, so to summarize, so a reaction that favors products has a large Kc because the products are in the numerator. A reaction with about equal concentration of products and reactants has a Kc close to 1. Again, to find really exactly equal concentration for all reactants and products is quite unusual. The equal in equilibrium has to do with rates, not with amounts. So again, the rate of the forward equaling the rate of the reverse reaction is what achieves equilibrium. The exact amounts being equal is quite rare. And then finally, equilibrium constant that favors reactants would be a small value for that Kc. So small, we'll say, again, less than 0.01, less than 100th would be a small number. And that can get very, very small, 10 to the negative 36, 10 to the negative 49 for the exponents, but it's always a positive value. For the large Kcs, again, here we'll say over 100, where reactants is much less than products in terms of concentration at equilibrium. It's almost a complete reaction, but still an equilibrium process because we still do have some unreacted, some reactants and some products at equilibrium. So there we have it. Again, if you need a rule of thumb, we'll say small is 0.01 or less, large is 100 or more, and between that 0.01 and 100, we're at an area where reactants and products are close in concentration, and if they're really truly exactly 1, then the reactants roughly equal the product concentration. Okay, so hopefully that helps to clarify this position of equilibrium and what the numerical value of Kc actually indicates. Here we see table 9.3 from the text, and again, the Kc is large. We've got 2 times 10 to the 11th, 1.1 times 10 to the 7, 1.6 times 10 to the 2. Those are all cases where we have mostly products, especially that 2 times 10 to the 11th. There's really almost no reactant remaining at equilibrium, but there is some because it's a reversible reaction. There's always going to be some reactant and some product. In this case, very little product, overwhelmingly very little reactant, overwhelmingly product. If we look down below, the last couple, 1.2 times 10 to the minus 2, 2 times 10 to the minus 9, these are examples where very little reactant has gone on to make product. When we achieve equilibrium, overwhelmingly we have a reactant present with very little product, especially in the case where it's 2 times 10 to the minus 9. But again, there is some product, there's some reactant, it's a reversible reaction. It just happens to find its equilibrium at a position where the reactants are greatly favored in terms of concentration compared to the products. All right, so let's just pause here for a learning check, make sure that these ideas about equilibrium and the value of the equilibrium constant are making sense. So in this learning check, you're going to indicate for each of these KCs whether the reaction at equilibrium contains mostly reactants or mostly products. So in the first case, we have a KC of 1 times 10 to the positive 95. In the second case, we have a KC of 1.8 times 10 to the negative 7. Pause the video here, make your determination as to whether reactants or products are favored at equilibrium for each of these reactions. Once you're ready, start us back up and we'll see how you did. All right, so hopefully for the first case, that's a pretty large exponent, right? 95, positive 95 exponent. So the Kc here is very large, and we have essentially products at equilibrium, just a tiny little bit of H2 and F2 reactants present at equilibrium. So overwhelmingly, we contain products. In the second example now, where it's 10 to the negative 7 for the exponents, we have a very small number, and that's an indication that at equilibrium we have mostly reactants. Overwhelmingly reactant at equilibrium, a little bit of product. It's a reversible reaction. We will have both. But in the first case where we had almost all product and very little reactant, in the second case we have almost all reactant, very little product. So hopefully that went well. Again, if you're struggling, there are a number of these you can try in the text, and certainly you can reach out to me for additional problems and guidance if you're still struggling. In addition to just looking at the Kc value and determining whether you have mostly reactant, mostly product, roughly equal amounts of reactants and products at equilibrium, you can also actually use the Kc expression to find an unknown concentration. So first of all, we'd have to write that Kc expression for the equilibrium equation. We'd solve the Kc for the unknown concentration. This means we'd have to be given the Kc numerical value itself, and we'd be looking for one unknown concentration, and then finally substitute in the known values, rearrange Kc to solve for that one unknown concentration and be able to calculate its molar concentration in the term of Kc. Okay, so let's see how we would calculate an unknown equilibrium concentration using that approach that we just reviewed. So in this case, at equilibrium, the reaction of PCl5 gas is an equilibrium process with PCl3 gas and Cl2 gas, and it has a Kc of 4.2 times 10 to the minus 2 as written, of course, so we're considering PCl5 as the reactant and PCl3 and Cl2 as the products. We contain a PCl concentration, PCl3 rather, that's equal to the Cl2 concentration, that's equal to 0.10 molar at equilibrium. So we know the product concentrations. We do not know the reactant concentration at equilibrium, so that's our question. What is the equilibrium concentration of PCl5? So we have the balanced chemical reaction equation, we have the numerical value of Kc, we have the equilibrium concentrations of the PCl3 and the Cl2. All we're missing is the equilibrium concentration of the reactant PCl5. Okay, so in step 1, we'll write the Kc expression. So we write it like any other Kc. Here it's an example of homogeneous equilibrium, so we have everybody in the same phase. Everybody's a gas, so everybody's going to be included. All the coefficients are 1, which makes life really nice and simple here. So the Kc will be the products, the PCl3 concentration times the Cl2 concentration, divided by the reactant PCl5 concentration. Again, they're all raised to the 1 power because they all had a coefficient of 1, so we don't explicitly see any of that. In step 2, we're going to rearrange to solve for the unknown concentration. So the unknown concentration PCl5, if we multiply both sides by PCl5 concentration, then divide both sides by Kc, we end up with the expression that PCl5 equilibrium concentration equals the equilibrium concentration of PCl3 times the equilibrium concentration of Cl2 divided by the value for Kc. Moving on to step 3, our final step, we'll substitute in those values. So we had a 0.10 molar concentration for both PCl3 and Cl2. So we substitute that in, multiply them together, divide through by the 4.2 times 10 to the minus 2, the numerical value of Kc. And again, because we are doing all of this with K sub C, the equilibrium constant with respect to molar concentrations, although we don't show units for Kc, we know they have to be right to give us a final unit of mole per liter, or big M, as we see here. And so the numerical part works out to 0.24. The unit is mole per liter, or big M, and that is our equilibrium concentration for PCl5. So hopefully now you see a little more clearly, if you weren't understanding before, how we can use equilibrium constant value and concentrations for reactants or products to solve for an unknown reactant or product concentration. Okay, let's go ahead and see how you do now with that idea by a learning check. In this learning check, you're going to find an equilibrium concentration. You're told the Kc is 2.0 for the reaction 2NOBr gas is in equilibrium with 2NO gas plus Br2 gas. If the equilibrium concentrations are NOBr concentration equals 0.50 molar at equilibrium and concentration of NO equals 0.80 molar at equilibrium, what is the equilibrium concentration of Br2? And you have some multiple choice answer options. Please go ahead and pause the video here, solve using our approach, and then select the correct A, B, or C letter choice, and then start back up, and we'll see how you did compared with what we find to be the correct answer. All right, so let's look at how we solve a problem like this. Hopefully you already know and you're just waiting to see if you were right. But what we know from the problem itself is we know the reaction equation, a balanced chemical equation. We know the numerical value of Kc. We know the equilibrium concentration of the NOBr is 0.50 molar. We know the concentration of the NO is 0.80 molar at equilibrium. We're looking now for the concentration of Br2 at equilibrium. According to our scheme, in step 1, we write the Kc expression for the equilibrium equation. So Kc is equal to the product concentrations multiplied together, each raised to its stoichiometric coefficient as a power, divided by the reactants multiplied together, each raised to its stoichiometric coefficient as the power. So in this case, we have NO raised to the second power, its concentration anyway, because it had a coefficient of 2 in the balanced chemical equation. That's now multiplied by the concentration of Br2 raised to the 1 power, which we don't show, divided by, we had just the one reactant here, so divided by the NOBr concentration raised to the second power because of its coefficient of 2, and that's all equal to Kc. So there we have our Kc expression. We know 3 of those 4, right? We know the Kc value itself, we know the equilibrium concentration of NO, and the equilibrium concentration of NOBr. So we have just our one unknown. It's a classic algebra problem now, and hopefully you're ready to move on to step 2, and that you've already done that correctly. Okay, here we are for step 2. We're solving that Kc expression for the unknown concentration. So if you remember what it looked like before, we had the Kc equals the NO concentration raised to the second power times the Br2 concentration raised to the first power divided by the NOBr concentration raised to the second power. In order to get Kc, rearranged in BR2 by itself. Since BR2 was in the numerator before, we multiply both sides by the denominator. The NOBR raised to the second power is now multiplied by both sides. And then finally, we divide both sides by the NO concentration squared to isolate BR2. And if we do that correctly, now we can just simply substitute in the values that we know. So the concentration of Br2 at equilibrium is equal to the equilibrium concentration of NOBr, the 0.50 molar squared, multiplied by Kc's value of 2.0, divided by the 0.80 molar concentration of the NO at equilibrium, squared because of its coefficient, and we end up with a final answer of 0.78 molar, which is answer B. So hopefully that's the answer you selected, and you get my kudos here. Good job. If that's not the case, either if you guessed and you got lucky with B, or you guessed and chose A or C, or you really didn't know what to choose or where to do this problem, please do try some additional practice problems from the end of chapter, and definitely reach out to me for some guidance if you're still struggling. Okay, otherwise, hopefully things are going well and you're ready for the last section of chapter 9, and we'll see each other for that lecture soon.